All right, today we're doing 8.3 logarithmic functions as inverses. So let's take a look at what something we already know and how to graph certain things already. So we know how to graph an exponential function right now. And for example, if we take y equals 10 to the x, we know that that is an exponential function because your x value is in the exponent. So we know that when it's y equals 10 to the x, or if it's in the form of y equals a times b to the x, and when the value of b is greater than 1, which in this case it is, b is 10, then we know it's an exponential growth. So we know that this is going to look like an exponential growth function. So let's graph some points here because later on we're going to be looking at the inverse of this. So if we plug in some negative values like -2, -1, we'll plug in 0 and some positive values. So for this we have 10 to the -2, which is 1 over 10 squared, or 1 over 100. Really close to 0, right? Because it gets closer to your asymptote of y equals 0. We have 10 to the -1, which is 1 over 10, 1/10. 10 to the 0, or anything to the 0 power, is a 1. 10 to the first is a 10, and 10 squared is 100. So we don't need to plot every point that we find, but we can plot the ones that will be helpful for us. So we have -2, 1 over 100, that's really close to 0. -1, 1/10, also really close to 0 here. 0, 1 right here, and we can plot some points here. Here's a 2, 4, 6, 8, and here's our 10. So 1, 10 is up here. Okay, so now when we actually go ahead and graph this here, we can graph that and kind of come up here and then go up, go down, and we know that this is exponential growth coming up, and then it also gets really close to your y-intercept of y equals 0. And then we can actually graph our asymptote here. So if we graph the asymptote, we know that that is going to be y equals 0. So we'll graph that here of here we go. So here's our asymptote of y is equal to 0. And this is important to put in just because then you know, okay, I'm not going to cross that line, and this is my asymptote of y equals 0. All right, and that's the asymptote. So whenever it's in the form of y equals a times b to the x, your asymptote is y equals 0. Before we move on, let's just talk a little bit about the domain and the range of this graph. So the domain here, or your x values, we were able to plug in any x value here, which just means that your x's are all reals. And for the range here, look at your y values. The y values, it's not going past 0, so we're not getting any negative y values. So for this equation, your y's are going to be greater than 0. Not greater than or equal to, because we're never touching 0. So just greater than 0 here. Okay, so let's get into some of the new stuff where we're looking at logs. So let's see. Here's what we got. So if we have something where it's y equals b to the x, we want to know how to solve for x. And some of you might have seen that in some of the previous problems where you had x as the exponent, and we need to solve that. So what you're going to do is you're going to use a logarithm. So the logarithm to the base of b of a positive number will be defined as follows. So this is color coordinated here, and we need to first get used to putting this as y equals b to the x in logarithmic form, which will just be log base b of y will be equal to x. Okay, and vice versa. So think of your log equations are equal to your exponent. So here's my exponent here, and that's going to be equal to that. Okay, so just take a look at where everything is. We have log base b, your base is a b here, of y, this whole thing is equal to y, is equal to x. And log equations are equal to your exponent. Your exponent was an x here. So let's first just get used to rewriting this in logarithmic form. So we're going to have two different forms here. One will be exponential form and the other one will be logarithmic form. So let's just practice this by taking 25 equals 5 squared. We're going to put it in logarithmic form. So we're just changing the form right now. So here's what we have here. So we have y equals b to the x is the same as writing log base b of y is equal to x. And this is what we're using. Okay, so we're going to write this in logarithmic form. So we'll write this as log. Okay, now I'm going to look at my base b. My base b here is a 5. So you write that as a subscript for your base of y. So your y here is 25. And it's equal to x, which is your exponent here, and the exponent is a 2. And that's writing in logarithmic form. Right now it kind of seems a little silly to write this in logarithmic form, but you'll see in the end or by the end of this lesson why we do this. So just getting a little bit more practice writing in logarithmic form. So we'll write this as log, my base is a 3, so write that as a subscript here. Log base 3 of 729 is equal to, remember log equations are equal to your exponent, 6. We'll do one more here. Log base 1/2, so that's your subscript here, of 1/8 is equal to 3. Okay, and so on. This one, real quick, log base 10 of 1 will be equal to 0. And we're going to look at base 10s in a couple slides here. Okay, so now we're going to take a look at evaluating the logarithm. So now we need to go the other way. So if it says to evaluate log base 8 of 16, well, we need to know what that's equal to then. So the first thing is to just set it equal to x, meaning we want to find x, okay? And then what you're going to do is you're going to convert it to exponential form. That'll make it a lot easier to solve it. So my base here is an 8, right? Base 8. Log equations are equal to your exponent. So your exponent is an x, and that's equal to 16. Okay, so now what you're going to do is you're going to get these to have the same base. So what you're going to do is you're going to say, what base can I make both of these have when I convert them? So if you make them both have a base of 2, that will work out. Because 2 cubed is 8. So, and then I still have my x. So I'm just rewriting it right now. 2 cubed is equal to 8. So I just rewrote that. And then 2 to the 4th power is equal to 16. So what I just did here is I just made them have the same base of 2. Okay? So, and this works out because 2 cubed is 8 and 2 to the 4th is 16. Okay, we know the rule that if we have an exponent inside and outside, we multiply them out. So I have 2 to the 3x power will be equal to 2 to the 4th. So now that we have the same base, once you have the same base, you're just going to take your exponents and set them equal. So we have 3x is equal to 4, and now we're going to solve for x. So I divide both sides by 3 here. That will cancel, and therefore x is equal to 4/3. So therefore, log base 8 of 16 is equal to 4/3. And you can go ahead and plug this into your calculator. You can plug in 8 to the 4/3 power, and that will give you 16. Okay, we'll learn log base 8 of 16 in the calculator later on, but that's just using a change of base formula. All right, moving on here. Sorry if it's noisy in the background. Okay, so let's take a look here. We're evaluating, we're going to do the same type of thing here. So I'm going to set this equal to x and change it to exponential form. Right now it's in logarithmic form. So my base is a 9, so I write 9 to the x power will be equal to 27. Now I'm going to say, what number can I make both of these have a base of? So they can both have a base of 3. So 3 squared to the x power, because 3 squared is 9, and 3 cubed is 27. So this will be 3 to the 2x. Some of you will want to skip this step. And then now I have the same base. So once you have the same base, a base of 3, you set the exponents equal. 2x equals 3, divide by 2, and therefore x is equal to 3/2. There we go. Okay, a couple more here. So setting this again equal to x, changing it to exponential form, we have 64 to the x is equal to 1 over 32. Okay, so this one is a little bit different because we have a whole number and then we have a fraction. So the first thing is to either make both of them whole numbers or both of them fractions. So what I'm going to do is I'm going to make both of them be whole numbers. 64 to the x will stay. And I'm going to make this 1 over 32. I want to bring that up to the top so it's a whole number. And I'm going to do that by writing it as 32 to the negative 1 power. Okay, and that's because 32 to the negative 1 power is the same as 1 over 32, right? Okay, so now what we're going to do is we're going to give these the same base. So in order to get the same base here, we need to figure out what can we make both of them have a base of, and they'll both have a base of 2. So this will be 2 though. We need to know that 2 to the 6th is 64, and then we still have it to the x, and 2 to the 5th is 32. Okay, so multiplying these out, 6 times x is 2 to the 6x, and 5 times the negative 1 is 2 to the negative 5. Now we have the same base, so now we set the exponents equal. We have a 6x is equal to negative 5. We divide both sides by 6 here, and therefore we get x is equal to a negative 5 over 6. We can plug this in. Negative 5 over 6, you can plug that in here and see if you get 1 over 32, and you will. And whenever one is a whole number and one is a fraction, you know that you're going to come out with a negative value here in the end. All right, moving on. Let's see. Okay, so let's talk a little bit about a common logarithm. So a common logarithm, what that means is it's going to have a base of 10, So you're going to write this, log base 10 of y will be written as log of y. So they're just dropping this base of 10. So if you see log of y or anything that does not have a base, then you know that it's a common log, which just means it's a base of 10. Okay, so let's get to graphing these a little bit, and I apologize for my horrible graphs ahead of time. So we're looking at a logarithmic function is the inverse of an exponential function. So we know that when we're dealing with inverses, we know that we're going to switch x and y, right? That's what an inverse does. It switches x and y. Okay. So we already graphed y equals 10 to the x in the first slide. So y equals 10 to the x, if we change that to logarithmic form, it will be written as we have log, our base is 10, of y is equal to your exponent x. But we know that if it's a base of 10, then we don't have to write the 10 in because it is a common logarithm. So therefore, that's why it has y equals y equals 10 to the x is the equivalent to log base 10 of y equals x, which is also equivalent to log of y equals x. Okay, so moving on now. Now we're going to look at the inverse. So as we just said before, the inverse is switching x and y. So the inverse now, if we take log of y equals x and we switch x and y, then we get log of x equals y, because I just switched the x and y. Which also means log base 10, right? Because if there's no base written in, it's a 10. Log base 10 of x equals y. And changing it to exponential form, we can write it as 10 to the y is equal to x. Okay. So we're going to go ahead and graph log of x equals y, but to do that, I'm really just graphing this because all of these are equivalent. All of the things in blue mean the same thing. They're just this in logarithmic form, exponential form. So here's what we're going to do. We're going to graph this, but if you notice here, 10 to the y is equal to x. If you notice, what happens is we're going to take whatever is in the exponent. So the exponent here is your y. So in order to graph this, the easiest way to graph this is to plug in values for your exponent. So what we're going to do is we're going to plug in values for your y and solve for x. Okay, so I'm going to plug in values for my y, -2, -1, 0, and 1, and now I'm going to solve for x. So this is 10 to the -2, 10 to the -2, which is 1 over 100. This is 10 to the -1, which is 1 over 10. This is 10 to the 0, which is a 1. 10 to the 1st, which is a 10. So now my x's are here, and I plugged in for my y. I plugged in for my y because that will be easier to solve by plugging in to your exponent and then solving for your x. So just like how we switched the x and y before, you switch everything. So now for these equations, your asymptote will change too. Your asymptote for y equals 10 to the x, the asymptote for y equals 10 to the x, the asymptote here, is y equals 0, right? So now the asymptote for our inverse also changed. So now instead of it being y equals 0, it's x equals 0. So let's go ahead and plug in our asymptote first. So we're going to plug that in. And when I plug this in here, let's see, use the red. Okay. So x equals 0 is the same as the y-axis, right? So here's my asymptote. I always like to plug in or draw my asymptote first because then I know, okay, I can't go past there. Okay, so now I'm going to plot everything. Here we go. So I have 1 over 100, -2. So that's really close to 0, -2. All right, somewhere right there. 1 over 10, -1, also really close to 0. 1, 0, and then 10, 1. Here's 2, and 4, and 6, 8, 10. So 10, 1 right here. Okay, so now what this will look like is something like the following. Alright, I know some of you are going to make fun of my graphs. I know, it's pretty bad. Okay, so we get the idea though. It's approaching our asymptote of x equals 0, and then it's going to continue going up. That is pretty bad, I admit it. Okay, so that's the idea of it. It's the inverse. You plot your asymptote, x equals 0. Plug in points for y now instead of x because your y is your exponent. All right, moving on. This is very similar. We're going to actually skip that because I don't want to make the video too long. Here we go. Okay, so now here's what we have. All this is saying is if we have y equals log base b of x, which is b to the y equals x, right? Then the inverse is y equals b to the x, okay? So meaning the inverse is going to be x equals log base b of y. There we go. Those are inverses. So this means the same thing here. And then this one means the same thing here because it's b to the y is equal to x. Okay. There we go. Okay. So now we're looking at, it says since 0, 1 and 1b our points on the graph of y equals b to the x. Well, let's make sure of that. Y equals b to the x, this one here. And that's because if I plug in 0 for my x, I'll get 1, because anything to the 0 is 1. And 1b, if I plug in 1 for my x, b to the first is just b. Okay? Then they just switch. This is just saying that for your inverse, you switch x and y. So inverse, we went over this, you switch x and y. That's what all this is saying, switch x and y. Okay. Since the x-axis is the asymptote of you guys can catch my spelling mistakes, of the graph of y equals b to the x, and the y-axis is the asymptote of y equals log base b of x. So let's take a look here. So we just said in the previous problem there that if we have y equals log base b of x, right, which is b to the y equals x, we know that the asymptote here is going to be your y-axis, which is x equals 0. Okay? And we graphed that before and showed it, right? It was the x equals 0, right? And it was approaching it like that. There we go. That's a pretty good graph. Okay, so now what this is doing is you still have the translations. The translation h units and k units, right? So now for this, if we have this asymptote, which is horizontal, which will be a horizontal move of changing it, so this asymptote, which is x equals 0 here, if we go left and right, that's going to be changing our asymptote. So now the h is what's going to be moving your asymptote. So your h value will move the asymptote. Okay? And the k value will not be. So it's opposite of the exponential graph. So your asymptote for y equals log base b of x, which we just did, y equals log base b of x, which is the same as writing x equals b to the y. The asymptote here that we just went over is going to be x equals 0. We just went over that. Okay, so now for this one here, we're going to take x minus h. This is going to be your asymptote now. So whatever x minus h equals 0 is. So we add h, and therefore now, here it is. Your asymptote for this graph is x equals h. Okay. So now if we look at the domain here, look at this graph here. If we look at the domain of this, we know that we don't have any negative values for x. So therefore, for this one, your x is going to be greater than 0 here. So your domain for this graph is just going to be x is greater than 0. For this one, if I move my graph left and right, then that's also going to change my domain. So my domain now for this will be x is greater than h. The range for this, look, this is slowly going down. Actually, it's going down fast, and it's going up as well. So your range for both of these is all reals. There we go. All right. Now that we got that filled out, let's do a translation. Here we go. So we're going to start with making a table of values for the parent function. So the parent function is y equals log base 6 of x, which is the same as writing 6 to the y is equal to x, right? So this is the same as writing all of that out. So x equals 6 to the y. Okay, so we know that when your y is in your exponent, plug in for your y. Plug into whatever your exponent is. So we'll plug in some values here. So we'll plug in -2, -1, 0, 1, so on. Okay, so we'll plug that in. So we're going to go 6 to the -2. 6 to the -2 is 1 over 6 squared, which is 1 over 36. Next one, we plug in -1. So 6 to the -1 is 1 over 6 by getting rid of that negative exponent, by bringing it down, so 1/6. 6 to the 0, anything to the 0 is a 1. And 6 to the first is just going to be a 6. Okay, so this is the parent function, the table for that. And now we know that we're going to take this and we're going to do whatever your h and your k are telling you to do. So this is telling us to go 2 units to the, we know that it's going to be the opposite when it's with our x value. So we're used to having the opposite there. So we know that we're going to have x equals 2 is going to be our asymptote. So you go 2 units to the right. And therefore, instead of your asymptote being x equals 0, your asymptote will now be x equals 2. So this is my asymptote. Okay? And this one here, the plus 3, is telling us to go 3 units up. So if we're going 2 right and 3 up, I'm going to add 2 to my x's, and I'm going to add 3 to my y's. So now we'll make a new table here. So here's our new table, our x and our y's. So we're adding 2. So 2 plus 1 over 36 is just 2 and 1 over 36. 2 plus 1 over 6 is 2 and 1/6. 2 plus a 1 is 3, and 2 plus 6 is 8. Okay, let's do it for our y values now. So we have 3 minus 2. 3 minus 2 is a 1. 3 minus 1 is a 2. 3 plus 0 is 3. And 3 plus 1 is a 4. So it should look like it's taking the parent graph and it's moving 2 units to the right and 3 units up. All right, so before I even graph these, again, I like to put my asymptote first. I like to graph that first, so it's kind of like a guide for me. So I'm going to graph my asymptote, which I know is x equals 2. So here's x equals 2, my asymptote. And now I have that as my guide to not cross. All right, sorry about the bell there. And so now we're going to graph all those. So we have, here are our points here, 2 and 1 over 36. 2 and 1/36, 1. So we'll go 2 and 1/36, 1. That's right here. Okay. 2 and 1 over 1/6, 2. So 2 and 1/6, 2. Also close to our asymptote. We have the point 3, 3 and 8, 4. So 3, 3. So 3, 1, 2, 3, and 8, 4. Here's 4, 5, 6, 7, 8. If that's right. 8, and that was a 4. So 1, 2, 3, 4. And here we go. Okay, so connecting these points and showing that it keeps getting closer and closer to your asymptote here, coming down. And then this one showing that it's going to start to increase pretty fast. And that is our logarithmic function. And that will wrap it up. We could do one more, but if we need more help in class, then we will do that. All right, that's a wrap. Thanks for listening. Bye-bye.